All right, so I'm going to try this again. I have a 25-minute video with no sound because it never started recording. So now I can see the record button in the corner here, and I know it's on. So here we go. This is Math 250, video number 8. And this is to be viewed on Wednesday the 17th. Is that right? No, the 16th. Wednesday the 16th. All right, let's do some recalling here. Recall from the last video. So we're going to let A be an M by N matrix. Okay. And we define the column space of A, call A to be the span of the columns of A. And we define the null space of A to be solutions to the homogeneous equation AX equals 0, right? All linear combinations of the solutions to AX equals 0. Okay. And then we also showed, this is more important, that so when you find the basis for the column space of A, these are just the columns of A that correspond to pivot columns, right? So to find the basis for the column space of A, you row reduce this thing, you look at the pivot columns, and the pivot columns from A, the original matrix, give you the basis for the space. And then the basis for the null space of A turns out to be the solutions, i.e. the free variable. It's really the free variable parametric solution that we've been doing. Well, if you were in DiffyQs, you've been doing it since February. Okay, so now we carry on and talk more about bases. So for a given subspace of Rn, which we'll call H, a basis for H is not unique. Right? So for example, let's just look at good old R2. The standard basis is the set of vectors E1, E2, or in vector form 1, 0, 0, 1, right? So that's a basis for H being R2, but so is any two linearly independent vectors. So here's another one, 1, 1, 1 minus 1. Right, here's another one, 1, 2, 3, 4, etc. So bases are not unique, and it's kind of nice because it gives you a lot of freedom for doing problems. All right, so today we're going to have two major definitions. The first one is this. So the dimension of a subspace H of Rn, which is denoted dim H with no parentheses, is the number of vectors in a basis for H. And so while I just said a second ago that bases aren't unique, they all have the same cardinality. In other words, every basis has the same set of numbers, number of numbers. Okay, so all have the same number. All have the same cardinality. So any basis for R2 is going to have 2 vectors. Any basis for R3 is going to have 3 vectors, etc. Okay. So, for example, 2 here, Rn has dimension n. Okay, so now we've defined dimension. Okay, so here's another definition. The rank of a matrix A which is denoted rank A is the dimension of the column space of A. Right, so you find a basis for the column space of A, you add up the number of vectors in that basis, and that's the rank. And you can't talk about rank without this other definition. The dimension of the null space of A is called the nullity. And as we showed before, the column space of A and the rank space, the column space of A and the null space of A are linked. And we'll see in a little bit. They're actually connected by a very famous theorem. All right. Let's get an example in here because that makes things much clearer. Okay, we're going to let A be the matrix. And this is 4 by 5. It's no fun if it's 2 by 2. There's not really much to say, so we're gonna go big here. So 2, 4, 6, 0. 5, 7, 9 minus 9. Minus 3, minus 4, minus 5, 6. Minus 4, minus 3, 2, 5, 8, 9, 4, minus 6. So this guy is a 4 by 5. Okay, we're going to find 4 things here. We're going to find the rank and nullity of A, and we're going to find bases. The column space of A and the null space of A, right? So all this is really linked, so it makes sense that we put them together here, right? Okay, so like almost every problem in this course, your first step is to get your computer out and find the row reduced echelon form of A. And when you do that, there's some fractions that appear, so it's not always going to be integers, you hope, but this one's not. At least there's no square roots. So the first row is 1, 0, 1, 6, 17 twelfths. The second row is 0, 1, minus 2 thirds, 0 minus a sixth. The third row is 0, 0, 0, 1, minus 3 halves, and the last row is a row of zeros. All right, so I got this from, from my solver, and we see straight away that there's a pivot column. There's a pivot column, and there's a pivot column. So we have 3 pivot columns. That means that the column space of A has a basis with 3 vectors in it. So So the rank of A is 3. Right? Rank of A is 3 because there's three pivot columns, which means there's 3 pivot columns, which means that this vector, this vector, and this vector all make up the basis for the column space of A. And there's 3 of them in that basis, and so the rank of A is 3. So let's find the basis for the column space of A. And it turns out, it turns out to be, where are those vectors? 2, 4, 6, 0. Second one is 5, 7, 9. And the third one is -4, -3, 2, 5. Okay. So let's see here. We have solved now. We found the rank of A, and we found a basis for the column space of A. So now we need to find the basis for the null space of A, and the number of vectors in that basis will be the nullity. Okay, so trying to keep everything here. With the row reduced echelon form, we see that what? We use green again. That this is a free variable x3, and this is a free variable x5. So we have 2 free variables. And that actually tells you that the nullities too, but we'll get there eventually. So let's solve, so now we solve AX equals 0, which if you've been with me since diffie-qs, we've been doing this now since February. Okay, so when I do this the same way every time, I write out all 5 variables, because x is in R5. And then the next step, I always write down the 2 free variables, or however many there are. So in this case, x3 and x5. And then the other 3 variables should be linear combinations of x3 and x5. And you get that from reading this matrix up here. So x1 turns out to be -1,6 x3 -17/12 x5. And x2 is going to be 2/3 x3 plus 1/6 x5. x3 is free, so it sits there. x4 is 3/2 x5, and x5 is free. Okay. Okay, and so break this up. We have -1/6, 2/3, 1, 0, 0, plus x5, -17/12, 1/6, 0, 3/2, 1. Okay, and so, you know, bases aren't unique. So if you were trying to match this to the back of the book, or if you loved me, you would choose x3 so that these fractions go away, and you choose x5 so those fractions go away, but it's not important. So the basis for the null space of A is just going to be this vector, or any multiple of it. And this vector. And so that the nullity of A is 2, because there's only 2 vectors in this basis. Okay. So, theorem which is 14 from chapter 2. If a matrix A has n columns, then the rank of A plus the nullity of A equals 5. This is huge. This is an if-then classic theorem, right? If A has n columns, then the rank of A plus the nullity of A is 5, right? So we have the nullity is 2, rank is 3, and 3 plus 2 is 5, which is the number of columns. Okay? And then theorem 15, which is an old friend of mine. It's long-winded, but it's very useful. So we're gonna let H be a P dimensional subspace of Rn, right? And clearly P is less than or equal to n, or it wouldn't make sense. So any linearly independent set of P vectors, and that number is important, is automatically a basis for H. So you get spanning for free. Right? So if you know H is P dimensional and you have P vectors, all you got to do is show linear independence. You get spanning for free, and it's automatically a basis. Similarly, any set of P vectors that span H is a basis for H, which means you get linear independence for free. But I can tell you from years of pain in coffee shops at midnight doing linear algebra problems, both in undergrad and grad school, it's always easier to show linear independence than it is spanning. So the real piece of this that you want is this, right? This guy is your friend, because showing linear independence is significantly easier than showing span. Okay. And all you have to do is show the one to get a basis, which automatically gives you spanning. So you never have to show spanning if you're using your theorems right. All right. And so that's it. I added some more homework problems to 4 from 2.9. There are problems 4, 9, 10, 14, and 18. And just to reiterate, I haven't been doing this, but section 2.8 had 8, 10, 19, 24, 25, 31, and 32. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 problems for Monday. Which I think is the 21st. All right. Have fun.